So what I'm going to present is in basically the global context of uncertainty quantification. You will see that reliability analysis is, let's say, one of a kind of those problems, where we generally start with a computer model that describes a complex system, and we have developed this model to be able to make predictions of the behavior of the system and possibly optimize that system or make decisions. In practice, however, in most cases, we don't know exactly the values of the parameters to use for the system, so that's why we introduce this probabilistic framework, this probabilistic modeling, typically by using random variables to represent the parameters, either the uncertainty, the lack of knowledge on some parameters, or the natural variability that can exist in some parameters. I will talk about random variables, but of course sometimes it's random field or time series random processes, so it can be quite complex. Then the next step in this framework for uncertainty quantification is to propagate the uncertainty in the input parameters through the model. That is, compute some statistical properties of the quantities of interest that we want to predict with our models in order to make decisions. So typically, we will compute maybe statistical model, probability distribution, or, and that's the point today, probabilities of failure. Today we'll be interested mostly in rare events where the systems actually does not fulfill its requirements. There is usually also an interesting step which we call sensitivity analysis. It's especially the case when the model is complex and the input dimension is very large. In that case, it's important to be able to find what input parameters are actually playing a role in this problem. That is, what are the important ones whose uncertainty actually drives the output uncertainty and probability of failure. Because as it was said, in most problems where you have here a high number of input variables, the dimension is high, but the effective dimension in most problems, if not all problems, real practically important engineering problems, this effective dimension is very small compared to the total number of variables. And this has some consequences on the efficiency of the algorithms. So as I said, there are different goals that you can have when you do uncertainty quantification. Just have a mere idea of, let's say, mean standard deviation of your predicted performance of the system. Sometimes you want to have an idea of the PDF, but here today we are focusing on computing probabilities of failure. Typically, failure here is considered as the performance criterion y, the output of my complex model, is greater than some admissible threshold. Could be also lower in certain cases, but let's formulate this way. So here, this, as has been already shown by Jason, means that we are interested, if this were to represent the distribution of this output, we are interested in the tails and in very small values of probabilities. So it's clear from those schemes here that, well, to compute this efficiently, you don't need the full distribution. You need to focus in the tails. So that I will go very fast. This is the standard formalism. We assume that failure for the system corresponds to, let's say, the output quantities of interest greater than some admissible thresholds. This defines a limit state function. Here, typically, the threshold minus the output of the computer code with the standard notation, negative values, that is, points x in this input space such that this function here is negative corresponds to failure domain and positive values to safe domain. And the goal is to compute this probability of being in the failure domain. So on this scheme here, assuming that all points would be the same importance, more or less having a uniform distributions on the parameters, this would be really the volume, the yellow volume divided by the total volume. Of course, in practice, those parameters have distributions that are not uniform, and so the volume, in some sense, of this failure domain is actually the integral of the distribution on this failure domain. And as that's been said already, it's a multidimensional integral, possibly high dimension. This domain here is implicitly defined by such a condition, so it's not easy to integrate. And finally, what we want to compute in the end is typically in the range from 10 to the minus 2 to 10 to the minus 8, so it's quite difficult from this point of view as well. Okay, so this being said, the purpose of my talk is to introduce surrogate models and more specifically Gaussian processes to help in computing those probability of failure for complex systems. First of all, I'm not sure how much familiar you are with surrogate modeling and Kriging or Gaussian process. So I will spend some time explaining what it is, because I think it's also general purpose, not at all limited to reliability analysis. And then I'll present how to use this in the context of structural reliability, involving an additional ingredient, which is active learning. So let's say it's a sequential or adaptive usage of these Gaussian processes. And then I'll show some applications. Let me start with a surrogate model. So what is a surrogate model? Generally speaking, it's just an approximation of the original computational model you have. So as was said already, the original model may be a complex finite element model, subsurface flow simulator in oil industry, whatever complex computer code that helps you predict some interesting quantities for your system. But typically, one run of such model can take minutes, hours, days sometimes. So when you want to do probabilistic analysis on top of this, then it's like in Monte Carlo, repeating many analyses, it just lasts forever. So the idea of surrogate modeling is to replace this true model by something that is sufficiently close to be able to reproduce the same behavior, but that will be basically constructed based on a limited set of runs of the true model that we call an experimental design. So it's like Monte Carlo, more or less, except that the size here will be very small compared to the standard simulation methods. But of course, you need something more, and the something more is that you will assume some general shape of these surrogate models that somehow assume some regularity in the model being understood here as the mapping from the input parameters to the output parameters. So more or less a mathematical function that is implicitly contained in your black box computer code, and that you can just evaluate point by point. So this is a list, non-exhaustive list of currently used surrogate models. Polynomial chaos expansions, very relevant and powerful. Basically, it assumes that you can expand the output as a polynomial series up to whatever degree with, well, fancy polynomials, so that's why it's called chaos here. It's not just second order quadratic polynomials, in such a way that you can really represent quite accurately the features of this model. There are other formats. I could have added here also artificial neural networks and others. I will focus today on so-called Kriging or Gaussian process modeling, in which, well, you will understand these equations in a minute. The point of all these surrogates is that once it's, let's say, calibrated based on a limited set of runs, then it's fast to evaluate. So here, typically, those kind of equations, once you have fitted the coefficients of the surrogate models, you can typically evaluate 1 million Monte Carlo sample in a matter of a second. So it's very efficient, and that's the idea. That if you really want to use whatever simulation methods, for instance, for reliability, where you have seen that we need thousands to hundreds of thousands of runs, you can replace these runs by the run of the surrogate. So just again, a few general statements about how to build this. We start with an experimental design. So we start to put points in the input space, usually in a way that covers at best the space. If we want to have an approximate model, a surrogate model that is, let's say, more or less good everywhere, that's the starting point. Typically using, for instance, Latin hypercube sampling. Then we run the output of the real computer code. And then we somehow post-process this data. So here it's really a data processing problem once you have run those expensive runs of the computer model through a specific learning algorithm. So each of the surrogates has its own learning algorithm, let's say, that is the thing that transforms the real runs into the coefficients that parameterize your surrogate. So here again, I've just put some names. I will describe again Kriging and maximum likelihood estimations, because here we are in context of Gaussian processes. Okay, let me start now with Gaussian process. So the idea is the following. we assume that this function, this map between the input parameters and the output, here I consider just one scalar output. Of course, this can be a vector or more complex objects, but just for the theory and the simplicity, I assume just one quantity of interest, the one that we would put in the reliability or in the limit state function. So we assume that this can be represented as a realization of a Gaussian process with some mean value here that we will parameterize with a set of known functions. So here, for instance, linear combination of the input parameters. Of course, we need the coefficients afterwards, these so-called regression or trend coefficients. And then here, a part which is a stationary zero-mean Gaussian process that is just introduced for the purpose of the method. So here, that is very important. I could have put this even bigger. This here, so far and for the next 10 minutes, Gaussian process modeling is really a way to replace a deterministic function by another deterministic function that is simple to evaluate. Okay, there is no uncertainty, no reliability. The fact that there is Gaussian written here has nothing to do with the uncertainty in the problem that we will handle afterwards. And very often there is let's say, a confusion here. So when I described in my big scheme input parameters that are random with distribution, this can be any distribution. The Gaussianity here is another step, let's say, or another level. Okay, so how do we now parameterize this more specifically? So we have to choose the trend. Simple way to do this is to assume just a constant that is called ordinary Kriging. But usually it's better to assume that there is indeed some trend that you can capture with a set of functions, typically linear functions or polynomial function, and this is called universal Kriging. So this is more or less like regression, if you're familiar with this. Now the second part here is a stationary Gaussian process, so it's completely defined here by the so-called autocorrelation function. We assume here that we have some variance that will be later on computed. And so the behavior of the Gaussian process is really related to the shape of this autocorrelation. One typical correlation function that is used in the context of Gaussian processes for surrogate models is this so-called Mattern autocorrelation function. So it looks quite complex here, but we usually use it for there are two parameters. One is, let's say, a shape parameter, and one is a length scale parameter. So this has to be fitted, this length scale, according to the problem. But the nu here is basically a choice. You can see that for nu equals 3/2, 5/2, and so on, the expression is actually very, very simple. It looks like this kind of functions here. And this family is quite nice because according to the choice of nu, you get more or less a smooth realization of the Gaussian process. Here are realization trajectories of such a process, which can basically fit more or less complex code. So here you could imagine that as a function of x, you have your computational model that for some problem is very smooth and for other problems could be very, very complex like this. You can see that just by varying the choice of nu and the choice of the length L here, we could reproduce very, very complex behavior. So that's really the force of such Gaussian processes. Also, when nu tends to infinity, so if you take larger value, it corresponds to square exponential, Gaussian autocorrelation function, so very smooth processes, whereas for a nu equal 1/2, it's very non-smooth. So you really cover all kinds of possible models. Okay, how now do we fit the parameters? That was the question in my big table. So as I said, we start with some points in the input space and the corresponding output that have been run. So here, this step, I will not discuss, is exactly like Monte Carlo. If you have, let's say, computer facilities, a cluster, each of these runs is separate. So even if each run takes 2 hours, if you have 100 cores, this can be done completely in parallel and is kind of pre-computed. Okay? Then, as I said, we assume that the function now that we want to approximate is a realization of that Gaussian process. But for this process, we know in specific points, xi's, we know the exact value. So we will now find the approximation, this m-tilde, as the conditional Gaussian process, that is, for any new point, here I call this x0, but it's basically the dummy variable x. For x, a new x, the approximate model will be considered as the conditional Gaussian variable of the random process, which was very generally defined, given the observed points. So you will see in a minute with plots that is quite easy to understand. But before, let's play a bit with this equation. So the Gaussian point here is just really for the sake of being able to do analytically a number of computations, because Gaussian vectors have a number of well-known properties. Especially if you look at this representation, in each point in which I have computed my model, I know by construction, in that point, the Gaussian process boils down to a Gaussian random variable with those property, this mean value and this variance. And I know that very realization, that is the outcome of my original computer model. Now, if I put all together the observations, that is the runs of the real computer model, and the unknown value where I want to compute or estimate or predict my surrogate, all this jointly forms a Gaussian vector of dimension n+1, where I completely know what is the mean vector and the covariance matrix. I don't detail all these equations here, but more or less you have to evaluate all your regression functions in the trend at all points of the experimental design. You have to compute the correlation matrix between all points, and so on and so forth. And if you have this, now this is a joint vector. Now, also by basic textbook relationship for Gaussian vectors, you can compute the conditional distribution of y0 given the observation. This I denote with a hat. That will be my predictor. And it's a Gaussian, conditional Gaussian is still a Gaussian variable. And we can compute analytically the mean value and the variance. So the mean value is given here, where you can see that the beta coefficients here, so the coefficients in the trend, we can show that they are obtained by more or less solving a generalized least square problem. So if there was no no Gaussian process, the linear regression would give you basically this equation. Oh, sorry. This equation with R is just identity. Now, if you have a weighted least square or general least square, you have this weighted matrix on top of this. And that would give you a linear regression type of approximation. And the Gaussian process ingredient brings this additional term, which is very nice because it helps you to interpolate your data. So it's not anymore regression that more or less fits some curve between points. It's really interpolating your points, and that's good because if you spend hours to get the output for a given set of input parameters, you want that in the end your surrogates also give you exactly that value when you use the surrogate. Okay, so it's interpolating your points. What is very good on top of this, any other surrogate models will give you this kind of equation, something similar. So for any new x, you can use this equation and get a prediction with that particular property here that it is interpolating. But Gaussian process also has another nice feature. It gives you a variance that is in a given point where now you use the surrogate. You not only get the prediction, so the approximation of the true model, but also some range of confidence in that value. Okay, this is given by this complex expression here. Again, I will not detail what it means here, but the properties is the following. If you take or if you evaluate this here at the points where you add data, where you computed your exact computer code, you get 0. That is, in those points, well, you are interpolating and you have no uncertainty because you have the exact value. But in between, for other points, these expressions give you somehow how accurate your surrogate model is in that point. And this looks like this here. So it's again a one-dimensional problem. You will see this curve many times. I want to approximate the blue continuous line here, and I computed this model, 1D model, just at the yellow points. So just putting this information x, y of the yellow points into this framework, I get an approximation here, which is the dashed line. So in this area, very good. In this area, very bad. Okay. What is clear is that based on this construction, Gaussian process construction, I also have on top of the approximate dashed line, I also have a confidence interval that I can compute, basically because everything is Gaussian. I can tell that in this point here, my prediction is here, but it can, I mean, with 95% confidence, it will be between two bounds, and the two bounds are this blue colored area here. So again, consistent with what I said before, at the points where I have information, the yellow points where I computed the exact computer code, there is no error. It's interpolating, and there is really no, I mean, it's exact. And in any point when I am a bit far away from the existing data, then it can be a bit wrong, but then also I have a big or large confidence interval, meaning that, well, in those two areas I don't know much, and this already rings a bell. If I want to do better, it's of course this confidence interval here tells me that I should put more information in those areas, that is, select points where I will run my original computer model in those areas. Okay, okay. So that's the philosophy. Now a bit more on how to estimate the parameters. Everything I said so far somehow assumes that you know the autocorrelation function. Of course, in practice, you don't know it. So what we do is that we select a family. Typically, I said the mattern is very broad, so it's a nice family to start with, very commonly used. But then there are other parameters that you must fit from your data, especially the theta here in the correlation is the correlation length, or the scale parameter. And this is very important. Whatever the scale or the value you put here, you will get an interpolating model, as I have shown. The problem is that if you change completely this number, in between 2 points, you can have something very smooth or something very oscillating that is very close to the true model or completely bad. So this cannot just be fixed arbitrarily. This has to be fitted again. How to fit those parameters? Well, again, we are in the Gaussian context, so we can use maximum likelihood estimation. As I said already, if you take all the points from your experimental design, so the real computer code runs, jointly they form a Gaussian vector, and you have one realization of that Gaussian vector. The distribution of that Gaussian vector is known up to the parameters theta and the sigma square here. So basically, as it's a Gaussian vector, you can write a likelihood for this Gaussian distribution, or here the negative log likelihood that you may recognize. And this now depends on the unknown parameters, but what is known is the data, the y and the f and the beta, everything, that is already known from the computer code. So you can solve these equations, part of it maximizing this, minimizing the negative log likelihood. Part of it can be done analytically. We have seen this equation already for the beta parameters in the trend. And in the end, the best fitting theta, you have to solve numerically something. So that's life. Okay, so let's see how it works. Oh, nice. Okay, let's start again. Okay, so as I said, I want to approximate this 1D function just for illustration here, and I can afford 6 runs. So I selected 6 values between 0 and 15, unfortunately randomly, so unfortunately 2 are very close and there's nothing in the middle here. What happens here, it's a typical way of describing a Kriging model, so I will use ordinary Kriging, a given kernel, and that's exactly the curve you have seen already. Just from the 6 point, I can fit this, let's say, dashed line, which is quite good in the range where I have information and very bad in between here, plus the confidence intervals. Now, the nice thing is that the range here, the size of this is exactly the Kriging variance. that I obtain from the computation. And it looks like this Kriging variance. It's equal to 0 at all points that I use. That's my construction. And then between points somewhere, it's big. So this gives me a way to find if I was able to just iterate, that is, start with a small number of computations and then increase, that is, add new points, where I should put the new points. Okay? So usually we start in practice with putting points uniformly everywhere in the input space. But this gives you a way to put new points in your model where it makes sense, where you have the smallest information. Okay? And this works this way here. So here, based on this previous, here, that's where I, let's say, in other words, how I would get the most of the information if I do just one additional run. And if I do this several times, you will see that the points are each time at the places where there is the largest error. And after a few runs, then basically I can perfectly fit the curve. I could have here in the 1D problem stopped even before, and there is almost no uncertainty anymore in the prediction. Okay, so that was the background. Now, let's come back to reliability analysis. How to use this? Well, the idea of the surrogate is really to replace a complex code by a simple equation and then do whatever you want. So typically here, we would replace, let's say, the limit state function, g, yeah, it's here, by a pre-computed Kriging surrogate, so this mean predictor I've mentioned already. And then replace substitute the true failure domain by this so-called surrogate failure domain that is just replacing g by this surrogate, okay? And then do, for instance, let's say Monte Carlo, very crude Monte Carlo. Why can I do this? Because here again, compute this equation by pure Monte Carlo. This has been shown by Yasson already. Works all the time, provided you can put here maybe 10 million points. But here now I can afford 10 million points in maybe a matter of a minute because evaluating this has no cost. So that's the very first application of Kriging back in 2005. But we can do more than that because as you have seen, we have in each point some confidence in the prediction as opposed to other surrogate models. So here we can define, based on the Kriging variance, we can define not only, let's say, a substituted failure domain, but somehow confidence bounds on that failure domain. And this is defined here by taking the set of points in the input space where mu plus or minus, let's say, 2 standard deviation of the Gaussian process is negative. So here it's becoming a bit tricky because we have 2 levels of probabilities that have nothing to do. Here, x is really each point in the input space. And what this means is that if x belongs to that domain here, it means that it belongs to the true failure domain with a 50% chance, but this 50% chance is about the quality of approximation of the surrogate. If I'm not happy with this, I can use this here, and it tells me that any x that belongs to this domain now also, belongs to the true failure domain with a very high chance, okay? Since the variance is positive, we have this kind of let's say, inclusion here, so meaning that we also have bounds directly. And this we can see on this 2-dimensional problem. The true limit state function is the gray one here. We call this hat function. And the failure domain will be this part. If I just use these few points here, I can fit a Kriging surrogate for which the approximate limit state is the black curve here. Not so good, okay? But on top of this, I can also have confidence intervals that are the green and the red one. And so I can estimate an average probability of failure based on the failure domain defined by the black line, but also bounds. You can see here it's very bad, so the bounds are very big. And that's the starting point to start to get better, that is, improve this in an iterative way. To understand what happens, we have to look at the estimators. So we replaced the true estimator that is put Monte Carlo samples and count how many fall into the failure domains. We replace this by counting the one falling into the surrogate failure domains. So if this is equal to this almost for all xk, then this would be very good. Okay? So the point here is not that my surrogate model has to reproduce exactly the value of the true limit state, but it has to reproduce exactly, or the best possible, the sign. In other words, it's a classification problem. So the Kriging model can be wrong in terms of magnitude, but the sign for different points must be good so that it works well. So this leads to this idea of adaptive Kriging. We start with, let's say, one small size experimental design, get a first Kriging model, like in the previous picture. And then we will try to find the next point to add in this experimental design so that computing information, computing the real code at those new points will give me information in the vicinity of the true limit state and then improve the full calculation. And then we will update the surrogate and do this back and forth. So that's the same thing, but in a more algorithmic way. We start with an initial design, and in each iteration, we train a Kriging model on the current experimental design. We compute the estimated probability of failure and its bounds, and if we are not happy with this, we will use a so-called learning function to decide where to evaluate a new point with the real computer code so as to enlarge the experimental design, update the Kriging, and continue. This is how it works here. So this is exactly the same problem, maybe more colorful now. This would be the approximate limit state. This is the, let's say, conservative bound, the non-conservative bound. And in between here, that's exactly where the true limit state is. So this area, I know now from my current Kriging surrogate, it's clear that this is exactly there that I should test new points or put new points and evaluate the true limit state function at those new points and then update my Kriging, okay? Because it's really in this area that I want to better characterize the limit state. There's no point to have more information here. Anyway, this does not play a role for the reliability. Okay, so you can see here, this is just a band, but we can have a so-called probability of misclassification, which is basically maximal around the true limit state, and that we can evaluate. So all this, the way to find points here and to decide which points to take, this is called enrichment criterion. And of course, at the current stage, I should have a criterion that I can evaluate based on my current knowledge. And my current knowledge is just my current surrogate, that is Kriging surrogate and its variance. It should favor points that are close to the limit state to improve the description around the limit state, and possibly not choose just one point, but a few points, assuming that I have some distributed computer facilities. So there is a full list here of different functions. This was a kind of a hot topic, let's say, a few years ago, from 2008 to 2013. Different people, mostly in parallel, came to the same ideas. In the end, all those learning functions are quite similar in efficiency. The most simplest one basically is this one. So it's just the ratio of the mean to the standard deviation of the Kriging surrogate, the current Kriging surrogate. And it's clear here that when this is small, I mean, this can be small if either this is close to 0, so that means that this very point x, according to the current surrogate, is really close to the limit state surface, because it's 0 is the limit state surface, or it's very small because this is very big, and this means that the uncertainty in that point is very large. So in any case, it's worth selecting these points where u is small to get more information. Actually, some people prove that this probability of misclassification I've plotted here is exactly phi of minus d. So it's similar to things that have been said in the previous talk. Okay, so how do we do this? Well, we again sample a big number of points, and we evaluate this. Again, evaluating 1 million mu g takes a few seconds. So I can use a huge Monte Carlo. We usually work in the standard normal space, as was said before, so we know the bounds and everything. It's standard Gaussian space. So we can really use, let's say, 1 million points and then select the best one or the few best ones that corresponds to the best enrichment. And so that's how it works. Now, again, on a simple example, this is the same function as before, and I more or less, and so I'm interested in this limit state, 5 minus this. So meaning that I want to be basically below this line 5. So if I do this, you will see that now, in contrast to the previous examples, the points will cluster around the 0 value of the limit state. So not everywhere, but just in this area, also here a bit because it was not too far away. But it's really this enrichment criterion favors new point in the area where we really want to have a good or excellent description of the function and the limit state close to its 0 value. Okay? Okay, so, well, this works. Some other developments we have done recently is to put a bit more information in the trend. Usually people use those methods really with just putting here a constant, and that's it. We realized that if we put more information in this part, typically polynomial representation or even so-called sparse polynomial chaos expansion, then we increase also the performance of the method. So I will show some results. There was no discussion with Jason before, but we used the same example from Warts, which actually did his PhD here with Ton. This is a very nice 2D problem and so-called system problem in which basically you have this funny star-shaped limit state surface and the failure domain is outside this. So it's, I mean, it's two-dimensional, but it has some complexity. So here, and that's to show, well, it's 2D, so it's to show how it works, but it's also to show the powerful of those Gaussian processes. We don't consider here each limit state separately and then the full stuff as a system. We directly consider the failure, the system failure limit state with the mean value of this. Okay, so this gives the fancy function. We start with a few points here in this 2D space, and then at each step, let me give you, yeah, at each step we start with these points. These points will give you a first surrogate. From this surrogate, we evaluate in a big number of points the enrichment criterion, and when it's red, it means, okay, that's the area where I should select the best new point. And then we put this in the model, and then in each iteration, we update the probability of failure, and here you see also how the surrogate will improve. So if we use classical kriging, what we observe is that the probability, I mean, the first, let's say, branch of the limit state is explored, then the second branch, and then when it's very good here, the probability is still not good, so it moves to the next branch, and after a while, the 4 branches have been discovered, and then you have convergence, the surrogate is good, and the probability of failure has converged to the right value. It's also worth mentioning here, sorry? Oh, okay, yeah, I'm 2 minutes. I've not so many points. The same can occur with PC kriging. The only difference is that we put more, let's say, knowledge in the trend, so now we explore the full boundary of the limit state surface more rapidly, and so basically we get the same results but with far less iterations. Okay, well, you want to see maybe real problems, so just to show you that it works for real problems, this is 10 dimensions here. It's typical truss problem in which we want to compute the deflection from finite element code, and we want that this deflection, or we want the probability that this deflection is too large. So I will not comment all these numbers, of course, but just to show you that a typical, well, accurate estimation by Monte Carlo would be referenced here like 1 million of points. Any simulation methods presented before is probably a few thousand, which is already very good. Here we can solve the problem in about 100, 150 up to 200 points. So it's similar in complexity in that case, which is really very simple, to the first order reliability method in terms of number of runs, so in terms of cost. The thing is that, well, you can see here we are not talking about accuracy in terms of, let's say, 1 or 2 digits on the limit state, on the reliability index, but we have more or less 1 to 2 digits accuracy in the probability of failure. Is it useful? I don't know. But the thing is that, I mean, we could have stopped way before this 150. So maybe with already 50 or 80 runs, the estimation of PF and beta would be, for practical usage, very good. This one is 21 dimension. I don't go to the details, just to show that it's variables of different distribution, correlation, and everything. And again, here, well, in that case, reference, it's a bit more complex. So what is called reference was obtained by form and important sampling up to getting a nice estimation of the probability of failure. And again, here, this is the convergence curve of the reliability index or the PF. So we, again, got quite far away. But if you look after, let's say, 150 iterations, that is 150 real runs of the finite element model, we get an excellent value. So, well, these are my conclusions. Surrogate models, generally speaking, are very good to replace complex model and also for reliability analysis. Everything I presented is available in our uncertainty quantification software UQLab, so I take 5 seconds to just mention this bit of advertising. You can see all details on our website. It's a MATLAB-based software which has number of modules to do uncertainty quantification. Reliability or structural reliability is just one module among others, including surrogate modeling, sensitivity analysis, and many others. We have about 1,000 users all over the world for now some 2 years. These are the people already using it, and somewhere yesterday, it took me 5 minutes to find it. Was it? Yeah, somewhere here there is Delft University of Technology. So with this, I thank you very much for your attention.